Okay, so we just finished setting up some classes for points, for arrays, for rectangles, and doing intersection testing between points, rays, um, rays and rectangles, rectangles and rectangles, things like that. So now we can do a quad tree. So we're going to make a class called Quadtree, and this Quadtree is going to take rectangles added. That's why we made the rectangle class first. So if you insert a rectangle into a Quadtree, if you have exceeded the number of quad trees, like let's say a threshold is 3, once you exceed that amount, then the quad tree will subdivide. These things get clipped. So if this was rectangle 1, all of these guys are still rectangle 1, but they're all recursively inserted into the quad tree. So doing clipping is kind of the most annoying part of it, and we're gonna need to handle that. And we have a vector containing the actual information on each one of these rectangles, so that if we get a hit here, it actually points back to our vector, the index in our vector of rectangles. So we can do things like change the color of it and things like that. Because our goal is the ability to do point contents. Hey, which rectangle is here? 1. Hey, which rectangle is here? Nothing. And we also want the ability to do a ray cast, a trace line, a line trace, something like that, so that when the person shoots a gun, it will say, this is the point of impact here. And also you hit, by the way, box number 1. So you can do things with it for our puzzle. And like I talked about in the previous lecture, which I just am continuing on here, there's really 3 things you need on your quad tree. You need to be able to build a quad tree. You need to be able to do point contents. Hey, what's here? What's here? What's here? What's here? What's here? It's empty space, empty space, empty space, lava, sky, water, that kind of stuff. And you need to be able to do a trace line where you can shoot a ray through the world and very quickly tell the user, this is the thing that you hit. What you want to avoid is the situation where you've got millions of boxes and your code is just saying, like, you're shooting a ray. Hey, did I hit 1? Hey, did I hit 2? Hey, did I hit 3? Because this gets very, very slow. And collision testing 1,000 rectangles is probably going to be too slow, even on, when you're checking so many times a second. Okay. It won't be called Raycast. It'll simply be called Raymond. Nice. Okay. So what we need is a recursive tree structure. Every leaf in a quad tree is a quad tree. Okay. And a quad tree can be empty. This is a quad tree. This is a quad tree. There's nothing in it. Players and aliens and things like that won't get added to the quad tree. And so we might have, to test a number of aliens for being hit. For example, if an alien was here, then we would need to register that as the hit instead of this point over here. And so, there's different optimizations you can do on these sorts of things to make them go faster. But as it is, I think we're just going to put the geometry of the world into the quad tree. The geometry of the world is a AABB, which means it'll align very nicely with a quad tree, and it also makes subdivisions very easy, so on and so forth. So let's do this. So quad tree, every quad tree contains 4 children quad trees. Okay, so we're going to have a quad tree called upper left, which is going to, and these are going to be pointers, mind you, named upper left. That's equal to null pointer by default. And we are going to have a quad tree called upper right that is also equal to null pointer by default. And we're going to have a quad tree called lower left that is equal to null pointer by default. And we're also going to have a lower right that is also equal to null pointer by default. And this is in the private section because main won't have any access directly to it. Instead, we've got some things in the public section. We've got a constructor, does nothing. And so our 3 main operations on a quad tree are build, basically insert into it, insert a box, insert a rectangle, point contents, what's at this point, and 3 trace line. Right, so let's start off with insert. This is the main thing that people usually care about, which is how do I build a quad tree? That's That's always the hardest part. Once you get that done, the rest of it's not too bad. And we should also have probably a threshold in here, maybe. Integer threshold defaulted to 0, I guess. Actually, 0 is terrible. Default it to 1. And then maybe our constructor will take a threshold. There we go. No, you don't like that? Okay, so the threshold is how many objects need to be in a zone before you subdivide. And this is a tunable parameter. So I'm going to just make it a parameter instead of hard coding it. Seems a little bit better that way. Yeah, 0 threshold would be an infinite, problem. So, and we also should have a notion of maybe what area we're encompassing. So let's have a rectangle that is our bounds. And maybe we'll pass that in too. So let's have a rectangle called new bounds. And bounds will be initialized to new bounds. And the reason for this is we could have it be infinite, I guess. But how do you subdivide infinity? I don't know. It's not clear to me. So basically, when if we say the bounds of this are like 0, 0 to 100, 100, like this, when we subdivide, we're going to split it at 50-50, right? And then everything from 0, 0 to 50, 50, 50 is going to go into the lower left quadrant. This is the lower left. This is the lower right. The upper left. This is the upper right. Okay. So if we insert next time at 30, 30, then it's going to go into here. You guys understand? So we kind of need to know what our bounds are so that we can subdivide properly. Okay. Initials. Oh, these things. Yeah. That's the more correct way of doing it. And the reason why is because like our bounds can be like a const, right? If your bounds are a const, the only way you can initialize it is using it like this. You can't put it into the actual constructor. Yeah. And the threshold probably should be a const as well. Let's just be real about that. Let's move it down like that. And there we go. Okay. So, let's insert something. Void insert. Should be void. We can make it. We can make it. We can make it. We can make it Boolean if we fail, right? Like, what if somebody tries inserting something outside of the bounds? You know what I mean? But not gonna worry about it. We'll just die. Okay, so we're gonna insert a new rectangle into the thing, and the rectangle is gonna be called const. Actually, const rectangle rect r, and then we're also going to be inserting a which index it is in our overall. We're going to have like a vector of rectangles. We're going to have a vector of rectangles and vec out there, and vec dot insert pushback whatever r. Do something like that, right? And so we're going to have a bunch of rectangles, and that's what we have in our game right now. We have a bunch of rectangles out in the world, And I don't know, 20, 20 to 22, 22. That. It's a 2x2 square from 2020 to 22, 22. Like that. Okay, and we're just going to have a bunch of. Why do you not like that? One more set of curly boys on there. There we go. If we didn't place back. No. Should work. Yeah, okay. Might need more constructors on them. Okay. So we're going to push all these rectangles into the vector. And the reason why we want this thing here is because when we shoot array through the world, we want to return, hey, you hit vector index 5. And then that'll allow you to grab the rectangle at index 5 and change its color or whatever. Okay. So push back R. Okay, so we're going to make a quadtree. Name tree. And so, right. So its bounds are going to be from 0, 0 to 100, 100. So the quadtree is going to cover the zone from 0, 0 to 100, 100. And it will have a threshold of 3. So anytime you exceed the threshold, anytime you have more than 3 people in a square, then it'll split. Okay. Supers. Okay, so we're going to add some people into this. So rect. Do all of this directly. So just add a bunch of different. We're going to add a bunch of different squares in here. So one's going from 1010 to 1212, one's going from 2020, 2222, one's going from 3030 to 3232, so on and so forth. Okay. So we got a bunch of people in here, and they're all going to be in sort of that southwest quadrant of the world. So we're going to have a bunch of boxes kind of like this in here. And then what this will do is this will trigger a subdivision, and then it will recursively insert all of these people into the bottom left corner, and then it's going to trigger another subdivision centered on 25, 25. Okay. And then we'll end up having 2 people in the bottom left, 2 people in the upper left, upper right, rather. Okay. So let's do this. So yeah, so we're going to add all of these people to the quadtree. Okay. So for size I equals 0, I is less than vector dot size I plus plus. We are going to say tree dot insert vector dot at I. And so what we're doing is we're putting the index of every rectangle into the tree so that if we have to clip it, all of the different parts of it will be able to point back to the index in this vector here. Okay. All right. So let's go ahead and do this. Nothing's overlapping. I think if you have things overlapping, it'll probably cause problems. Yeah, if you insert like 4 people on the same location, you can't subdivide to split them up, right? It's just going to go into infinite loop. So we should probably reject anything that overlaps, maybe. I don't know if I'd like that. But we probably should. If any of the rectangles overlap, we should just throw them away. Okay. It's like let's actually test for that, maybe. So we'll add 2 rectangles on top of each other. And if we detect an overlap, just die or throw it away or something like that. Okay. So let's do this. Okay. So if our children are null, then we're currently empty, right? We should also probably keep track of like how many people we have. Int contains equals 0, right? So when we're first made, we don't have any rectangles inside of us. Okay, so if we're doing our first insert, if contains equals 0, in other words, if not contains is our first insert. If it's our first insert, then we need to new the four subquadrants. So we need to figure out our center point. Fortunately, we have a function to do that already. See previous lecture. So bounds dot center point. So vec2 center is equal to our bounds dot get center point. Just waiting for the ID. Nope, you didn't give me the parentheses that time. Great. Bounds add fonts actually to a lot of these people here. Add fonts to you. There we go. Everything's good now. Okay. So we're gonna need our center point, and then the bottom left corner. Okay. So so let's do the bottom left corner first. So the bottom left corner is going to be equal to a new Quadtree, and let's just make the, rather than passing this around every time, let's just hard code it. Whatever. We can make it adjustable in the future. I'm not going to worry about it. Okay, so we're going to make a new Quadtree, and we're going to pass in the bottom left corner. So if our center point is at 50-50, then the bottom left one is going to range from our bottom left to our center point. Yep. So it's going to be the min bounds dot min is its minimum point, and center point is the new one. And okay. And then for the lower right, it's going to be this point here and this point here. So it's going to be our center point x for the minimum, and our bounds minimum y as the bottom left point, and then the upper right point here is going to be center y for the y part and our max x. So we need this point here and this point here. So our bottom left corner, okay, so our bottom left corner is, we're going to have to actually, it's not going to be quite so nice as the first one. So our bottom left is center.x, min.y, and then our upper right is going to be max.x, center.y. Bounds. Like that. Okay. So we need that point and that point. Then for the upper left, the minimum is going to be U and U. And so this is our minimum X and our center Y. And then this one is our center X and our max Y. So this is our upper left. So it's our minimum X and our center Y. And then center X and max Y. And then for the upper right, that should be another easy one. So for the upper right, it's just going to be this, for this rectangle here, that's our bottom left, that's our upper right. This guy is just called max, this guy is just called center point, so we just pass in center point and max. Okay, so OIP, upper right, so you've reached the point where center no longer looks like a word. Okay. So the bottom left corner is the center point. And the upper right corner is max. There. Okay. And what we're going to do is we are just going to see out these values, I guess. All right. So OStream operator double arrow. So we're going to make the ability to print a Quadtree out. OStream by reference outs. Const Quadtree by reference Q. And we're just going to print out return outs Quadtree. Q dot bounds tree, and then Q dot bounds dot min dot X comma Q dot bounds dot min dot Y Quadtree, yeah, just min max Q dot bounds dot max dot X comma Q dot bounds dot max dot Y close parentheses. Call it a day. We can add other things about like our capacity and things like that later, but I just want the ability to just print these things out. Okay, so we're just going to see out LL lower right, upper left, and upper right. Just going to put these in the order that I use them in. Lower left, lower right, upper left, upper right. That seems right. So this should only trigger once. Oh yeah, because it contains. Yeah, we haven't actually added anything yet, right? But contains. We'll just increment that, so it should never happen again. Okay. So there we go. So min 0, 0, max. This is the upper left, lower left, right? So from 0, 0 to 50, 50. Lower right is 50, 0 to 150. Upper left is 0, 50 to 50, 100. Good. And then the upper right is 50, 50 to 100, 100. Good. We subdivided correctly. Neat. Okay. And so every time we recursively subdivide, it's just going to get our current bounds and then divide them in two and then repeat. Okay. So that's probably the hardest part of the Quadtree, is just getting that thing done. We'll also need a destructor, I guess. We're calling new. Or we can use smart pointers. What do you think? You guys want to use smart pointers, or you want to do it the old-fashioned raw pointer way? So you did binary trees, right, Megan? So the binary tree, every tree contains 2 children. This one, every tree contains 4 children. And all right, see you, Sean. So, so do you know new and delete, right, Megan? Like, so if we were to do this like with a standard destructor, get caps lock on. It's just lagging. Caps lock is on. Okay. All right. So if we do this with a standard destructor, Quadtree, when this guy goes away, we'll just say delete lower left, lower right, upper left, upper right. And if it's null, nothing happens. If it is got something there, then it'll recursively delete, and we'll be fine. So I'm just going to leave it at that. I think I'd rather use a smart pointer, but either. Okay, so I'm just testing to make sure. I'm just testing to make sure right now that we're subdividing correctly. So do you understand, like conceptually, Megan, what we're doing? Like we've got a quad tree that goes from 0, 0 to 100, 100. And then after we insert something, we have to cut it up into 4 pieces. And we're newing each one of the 4 pieces, and we're just figuring out the quadrant, the coordinates that each of the 4 children have. So that, like, we haven't added any rectangles or anything yet. All we've done is right before we add the rectangle, we have to new all 4 of the children, because right now they're all null pointers, right? We can't put anything into them. Okay. So, so whether or not you use a raw pointer or a smart pointer inside of a data structure like this it's not really the biggest deal in the world, because I'm controlling all of the access of the pointers. I'm not passing these out to anybody. Main can't see if I'm using a raw pointer or not. So, you know, I'm not too concerned about it, honestly, because I can basically guarantee every new has 1 delete. I'm good to go. Okay, so good. So we're dividing everything up correctly. All right. So what we're going to do now is we are going to figure out what quadrant the rectangle's in. And let's do this at first by just assuming that the thing isn't going to clip, because clipping is the hardest part of this whole thing, right? So if we're going to insert a rectangle that's going to span one of these intersections, we're going to have to cut it into 2 pieces or 4 pieces, depending on which intersection it's on. If it's outside of the rectangle, oh, we need a test for that, actually, right? So, so if does not intersect, so if our bounds dot is overlapping with R, so if it does not intersect, we just return. And thank you, IDE, never change, is overlapping R. When I don't type anything, okay, we just return. Or maybe print out. Error. R is outside of our bounds. Understand? So we're our quad tree is covering 0, 0 to 100, 100. If we try inserting something at 1,000 and 1,000, way over there, it's just going to print out error. You know, you're trying to insert something outside of my bounds. And we return. Okay. Little sanity check there. All right. So what we're going to do now is we're just going to try and figure out which quadrant, right? So if we insert like 10, 10 to 12, 12, like one of these squares down here, that has to be in the bottom left quadrant, right? And so we can have a Boolean left is equal to, and we're just going to use, like I said, we're not clipping yet. We're not handling clipping yet. We're just going to assume the whole thing is contained within one quadrant. So we just pick any of the points. So I'm going to say r dot min dot x. So if its minimal x location is left of our bounds, or center point x location, then it is going to be in the left half. And our lower. And then the same for y. So if they're below our midpoint, they're in the lower half. If they are left of our midpoint, they're in the left half. And then between the true and false for left and lower, we get all four quadrants. Okay. So if left and lower, we're going to say let's see here. Actually, not doing this right. What we really need to do is this, right? We really need to do this. If contains is greater than threshold is really what we need to do. But okay. Yeah, this is not correct. Okay. So if left and lower, then we are going to insert into the left, right? See what we're doing here? And not lower, then it is going to be upper left. If it's not left and it is lower, then it's going to be lower right. And if it is not left and not lower, then it's going to be upper right. Okay. So, but here's the problem, right? This is going to just immediately recursively go on iteratively forever, right? Because we only want to actually subdivide when we've exceeded our threshold. So we actually need at some point to be able to store a rectangle. Okay. And so we need actually here a vector of rectangles called data. And so until we exceed the threshold, we're just going to maintain like a vector of all the rectangles we've seen. So the first time you insert a rectangle into the Quadtree, we just store it. And second time you store it, and the third time you store it. And the fourth time, then you are going to subdivide like this. And then you're going to take everybody in data and shove them off in your kids and throw away data, essentially. So if so we're going to do, actually don't need you anymore here. Okay. Okay, so what we're going to do is this. So we're going to say data dot push back. Data dot push back. We need to save its tag too, huh? Maybe we can make tag like a property of a rectangle. We don't have to track it separately. We'll just do this. This is terrible. This is bad coding stuff. We'll do this. Okay. Integer tag index in the global vector of boxes. Yeah. And this is going to break everything, isn't it? Actually, okay, it handles it fine. Okay, so basically the first time we get a rectangle, so we're just going to keep inserting into our data vector until And until, we'll just have to give these guys a tag here manually. Like I said, this is not good coding style. But. There, just tag them that way. So as we put them in the tree, we just give them a tag and send them off. Okay. And the reason for that is, again, so that when our quad tree gets a hit, it can say, hey, this was index 5 in the vector. And then you can do something with it. Okay, so when we first insert into our thing, we're just going to say data dot pushback. This is going to copy the rectangle in, and we're good. Now, if we ever exceed our threshold, so if data dot size is ever greater than threshold, then we're going to subdivide. Okay. That makes sense? So when we start off, we're going from 0, 0 to 100, 100. We insert 10, 10 to 12, 12. Good. Insert 20, 20 to 22, 22. Good. Insert 30, 30 to 33, 33. Good. Then when we insert our fourth one, that's when we are going to subdivide. We've got 4 people in our data vector now. Now we have to iterate across the whole thing and recursively insert them into our kids. And so the bottom left one's actually going to immediately trigger another subdivision, but that'll be fine. Okay. So, so when we exceed the threshold, we create 4 subtrees, and then we're going to do a for loop. So we're going to say for every rectangle in data, for every rectangle in data, we are going to rect data. Ours is actually fine there, I think. It's going to shadow it, but yeah, it's fine. So it is going to recursively insert every person in the data vector. So all of the boxes are going to get recursively inserted into the 4 kids based on which quadrant they're in. And then we say data.clear, and we throw away our vector. And then we probably want to have a Boolean at this point. Saying we're full or something like that. Boolean subdivided is false. Okay, so if subdivided is true, if we've already split into 4, then what we're going to do is just this. If we've already split into 4, every time we get a new person, we just pass it on to our child. We could probably pull this code out and do a little bit better. But whatever. All right. And then otherwise, we'll do this stuff here. I think that should be about good to go. We got everything now except clipping. So if we've already cut ourselves into 4s, then we just pass it on to our child, and then they handle it. If we ever exceed our threshold, then, we need to set data.clear and subdivided Yeah. All right. Let's try this. See out. Subdividing. And we got two subdividings. Once for the top level, and then because all four were in the bottom left quadrant, that one then immediately subdivides again. And at the end of the day, we're going to have two people in the bottom left down here, and two people in the bottom left upper right over here. So maybe min max. Maybe outs for every const rect r and data outs r. So we're going to print out our boundary, and we're going to print out all the rectangles that are within that boundary. For every rectangle in Q.data. We need a double left arrow operator for rectangles. Go over here. Let's do that real fast. Let's make a output operator. Rectangles friend ostream ampersand operator double left arrow ostream reference outs const rect r. And this will just see out outs. R dot min, comma, R dot max. And then it's like, oh, but you don't have a point. See out. Okay, let's do that. Let's make a point. See out. So friend ostream reference operator double left arrow ostream reference outs const point ampersand p, and we will return outs open parentheses p dot x comma p dot y close parentheses and call that a day. Not a point anymore. They're called vect2s now. Cool. Okay, so we can print out a point. We can print out a rectangle. We can print out a quadtree. Everyone should be happy. So we print it out, and then we can say, see out subdivided. See out subdivided. Cool alpha. Q dot subdivided. Okay, so we'll print out our threshold. How many elements are currently within that quadtree, and if it's subdivided or not. Okay, so so let's insert 2 if I equals 2, see out the quadtree, and then at the end of the day we will see out the quadtree again. It's not recursive, so we'll probably have to do a recursive print. Okay. So we start off, minimum is 0, maximum is 100, and we insert 3 guys into it, 10, 10 to 12, 12, 20, 20 to 22, 22, 30, 30 to 32, 32. And so threshold is 3, contains 3, everything's fine. We have not subdivided. We insert one more person, it subdivides, it recursively subdivides. The top level now has a threshold of 3 that contains 0, but it has subdivided. So any future inserts into it just get passed on to the children. So we need to see out its children then. Okay, so if we have subdivided, then so if we have not subdivided, it'll just print out subdivided false. If we have subdivided, then we will print out all the children. Right child, upper left child, and more complicated printing. Like the printing's as complicated as anything. Okay, so up here, very first time we print it, subdivided is false. We then insert the fourth person. It subdivides the bottom left corner. It subdivides again. And then when we print it, our top level here goes from 0, 0 to 100, 100. It's got nothing in it. And then it prints out the children. The lower left child goes from 0, 0 to 50, 50. That one has also been subdivided, so it just stops there. Prints its children. So the left child of the left child, the lower left child of the lower left child, contains two boxes, the 1010 to 1212, the 2020 to 2222. The lower right has nothing in it. The upper left has nothing in it. And the upper right has, right, it has that duplicate box. So we need to, not allow. So, yeah, that's something we need to fix. But yeah, this is all correct. Everything is actually working exactly as planned, even though it might be a little bit hard to decipher from what's happening here. If you follow the logic, it's really important to be able to print your stuff out and kind of see. Maybe if it is not, we'll do this. So I don't think the threshold matters. If you've already subdivided, you don't need that anymore. So we'll just print that there instead. Okay. Okay, everything's fine except we need to not allow anything that overlaps. So if the new guy overlaps any of our current guys, we have to reject. So let's do a little check here. So for every const rect r in data, we can't call it r, array rect, I don't know, R2, names are hard. Okay, so if is overlap, r dot is overlapping, it's gonna do this. I know it is. Nope, yep, there it is. Okay, if it's overlapping R2, so if the rectangles overlap at all, then we see out error overlapping rectangles is not allowed by the order of the king. Let me just return. Okay. So if we ever insert a rectangle into the Quadtree where it's going to touch an existing rectangle, we just don't do anything. We'll print a diagnostic message, and we could probably give a better diagnostic than that. But this is going to prevent us from a degenerate situation where if you insert something, let's say here, like 500 times, the thing's going to subdivide and then subdivide and then subdivide and then subdivide and then subdivide and subdivide. It will never end because they're all on top of each other. You can't subdivide them apart. So this is stopping essentially an infinite loop. Okay, and we could probably add some more safety features by like making the minimum size, like have a minimum size of the Quadtree, so it can't go smaller than 1 by 1 or something like that. But I think this will probably be fine. Okay. So if we do this now, then when we compile it and run it, we get an error message saying overlapping rectangles is not allowed. And so down here, we see that the upper right quadrant of the lower left quadrant, this area here, no longer has that duplicate box in it. So everything's good to go now. Everything is good to go. Everything's fine. So that is everything you need to know for a Quadtree, except for clipping. Okay, and so clipping is fortunately this is about as easy as clipping gets. So if you insert something that is over a boundary, you got to cut it in half, and you got to put the parts in the upper half up here and the parts in the lower half down here. And yeah, all right, so every person here, we need to clip, possibly. So if the left is true, and the right is true, then we have to split horizontally. Okay. So let's do this. 4S right. And YYP lower, 5S upper. Okay, so this means our rectangle is to the left. The left half of our rectangle is to the left of the center. And this is true when the right half of our rectangle is to the right of the center. Now, ideally, the left and the right are both to the left of the center. That's what we've been assuming up till now. But it's possible the left is on the left side and the right is on the right side, and now you have to cut it in half. So if left is true and right is true, we have to cut this rectangle into two. And if the lower and upper are both true, we have to cut it into 4. So okay. Easiest way of doing this would actually be to just insert the halves into data. That breaks a range-based for loop, though. If you insert something into a vector while you're iterating through it, it screws up the iterators sometimes, and you don't want to do it that way. So we'll probably need to redo this as a regular for loop. I is less than data.size plus. And then we will just set our reference R is equal to data.at I. Okay, so we're going to just grab R, and then if we have to split it, we're not going to insert it. We're going to insert the splits instead. And we can just add them, I think we have to handle all the combinations here. There's got to be a clever way of doing this. Just trying to think of a way that can minimize the lines of code. Half and then recurse down into it, and then split those in half and recurse down into them. Something like that. Well, let's do it with more code. Why not? Okay. So if left and right are both true, make more booleans. Bool. Vertical split is equal to left and right. Bool horizontal split is equal to upper and lower. Okay. So if left and right are both true, we have to split it vertically on the vertical line. And so if we have a rectangle like this, left is true, right is true, lower is true, upper is true. So we have to split it 4 ways. So there's 4 possibilities. No splits, 2 splits horizontally, 2 splits vertically, or 4 splits where you're splitting it into quadrants. If not vertical split and not horizontal split, then we just do what we're doing. Else if vertical split, so we're going to have to split it into 2 halves. Split into the left half and the right half. So make rectangle left half is equal to so again, you have to go back to this thing here. Here's your center point. Here's your minimum point here. All right, see Megan. You can finish watching this later. This is, you got to bring this into the Raylib assignment. Yep. All right, peace. Okay, so minimum and center point. Okay, so this rectangle here is going to go from min x to center x this way, and from min x to max x this way. Max y rather. Max y is this way. Min. Okay. So the 2 points of this rectangle are here and here. Okay. So that is min x and min y is that point. This point here is center x and max y. It's that point. r dot min dot x comma r dot min dot y, bottom left half, and then center dot x and r dot max dot y is the other thing. And then for the other half of the rectangle, the part over here, this one, it's going to go from here. Let's do it in a different color. It's going to go from here to here. And so this guy is center x comma min y. That's that point there. And this point here is our max x comma max y. Handwriting is too bad. Too many. This point here is max x max y. X, minimum y, all the way up to r dot max x, r dot max y. Okay. And then we'll say data dot push back left half, data dot push back right half. So what's going to happen here is rather than recursively inserting it immediately, we're just going to add them to the end of the data structure. And because we're doing a for loop now, the size will update every time through the for loop. Hopefully it's not going to hoist that out. It shouldn't. And so what will happen is the current rectangle just kind of gets ignored. It'll get thrown away in a second. In fact, when we delete the entire vector, this rectangle is going to go away. Oh, we also need the tag installed here as well. R dot tag. And that'll pass on the ID. So even after we cut it, if this whole thing here was like rectangle 7, and we've made kind of 2 new rectangles here by clipping it into 2. This guy's still rectangle 7. This guy's still rectangle 7. And then what's going to happen is the left half, well, assuming it's not, we're not handling the, no, we're just cutting it like this, really. We're not over the center point. That guy. And then hopefully it's not, we're not going to get in rounding error, and the edge of this is going to be on the right side. Could happen. Floating point numbers suck. And so we might need to like adjust the boundaries in a little bit or something, pull them away from the edges, but we'll see if that happens. So yeah, basically, even though this whole box here was, tag 7, in other words, index 7 in our global array, even though it's being cut into 2, both of these guys are still going to point back to 7. So if we have a person shoot array here, it's going to report, oh, you hit this person here. That is box 7, and then you can do things with box 7 back in the global array, and do things like change its color or delete it or whatever. Actually, we probably shouldn't delete it. So then we'd have to rebuild the whole Quadtree, but you can definitely mess with it. And then we just need to do the same thing for horizontal cuts like that. So if we have box 8, then the upper half and the lower half are going to be box 8 as well. And yeah, let's just do that real fast. Okay, so also vertical split and not horizontal split. Like I said, I keep thinking there's got to be a way of cutting down on the amount of code here, because we're going to end up with 4 cases, and I feel like if I did this a little more cleverly, I could actually get it all into one thing, but whatever. I've clearly not had enough coffee yet today. Else if not vertical split, but we do have a horizontal split, then we are doing a cut like this, or we have a box like that. So it's not being cut on the vertical axis, it's being cut on the horizontal axis in 2. So we need to cut it into 2 halves. And so this original box here, it's going to have a pair of endpoints. So the bottom half is going to have those 2 endpoints, and the upper box is going to have these 2 endpoints, like that. So this is min x and min y, and this one is max x and center point y. This one here is minimum y, minimum x, sorry, center point y, and then this one is max x, max y, which I'm not even going to bother writing. Max x, max. Okay, so with that as my guide, I'm just going to put it on my other monitor over here. Then we're going to make 2 rectangles. Y, we'll do y4y. Paste, and we're going to have the 4s upper half. We're going to have the 5s lower half. Okay, so the upper half is minimum x and center y, and then the upper right part is max x, comma, r dot max dot y. The lower half goes from r dot min dot x to r dot min dot y. So the min x, min y, and then max x and Okay, and then last case is we're cutting it both ways. And we do this. Or if we don't even need to do this pushback, actually. Because we know where it's going, right? It's going to the left half. It's going to the left half and it's not being split. We actually could probably just do the inserts. And then we don't have to worry about the potential infinite loop from rounding point errors. So I'm actually going to do this a little more properly. Okay, so if it's in the left half, here, the new part, we just have to check to see if it's in the upper half or the lower half. So if lower LL dot insert left half, lower right dot insert right half. Maybe this is making it even more complicated, but at least we won't have an infinite loop. 2i, else it's in the upper half. See, by adding it to the data structure, like the data vector, it would just reuse our logic and just do it properly. But I'm nervous about floating point numbers. If you have numbers like you get rounding errors, and if you keep hitting like an edge over and over again, it'll keep cutting it. Because we're cutting it right on, like we're cutting it right in half, and I don't trust that it won't loop forever. So I'm actually just going to go ahead and do it like this. Okay. So if we're splitting it like this with an upper, like this horizontal cut, if we're on the left half of the world, we're going to put this into upper left and lower left. If we're on the right side of the world, we're going to put it into upper right and lower right. So if we are on the left side of the world, then we have lower left, upper left, and lower left. Like that. So if we're on the left side of the world, the upper half goes into the upper left, the lower half goes into the lower left. This is why I said clipping is kind of a pain, right? You saw the code earlier for just inserting it. If it doesn't clip, is fine. It's not honestly that difficult. But now we have to think about slicing it horizontally, slicing it vertically, slicing both horizontally and vertically, and no slices at all, which makes it just kind of annoying. And this is one of the easiest clips to make, right? Because we're clipping a rectangle that's axis aligned. We don't have any weird, star-shaped things that have to be cut potentially more ways than one. And then else, we're on the right half of the world, in which case this will be the upper half goes into the upper right quadrant and the lower half goes in the lower right quadrant. Now we don't have, now we can actually go back to range 4 load. Okay, so for const. And then finally, we're cutting it into quarters. So we've got a box that is overlapping the center of the quadtree. So our quadtree is like this, and we've got a guy like this, and we're gonna have to make 4 boxes, going from here to here, going from here to here, going from here to here, and this is literally the same math that we did for the quadtree subdivisions. So the good news is we can probably actually just reuse that logic up here. All right. Acceptance of bounds. Just gonna reuse that same logic there. Okay. So rect lower left is equal to you're mad at me? Bounds min vector double. Rectangle. Okay. So the bottom left part here, that guy is the lower left of the not bounds, not bounds, not bounds, not bounds, not bounds. R is minimum x, minimum y, and then the center point for the upper right. Pass in the tag. Okay. And then for the rect lower right, it's going to be equal to so I'm just going to change bounds R. Okay. And then right. Making sure to pass that tag to everybody. And did I forget something? Probably yes. You need one of those. You need one of those. You need one of those. And we're good to go. Okay, so the lower left quadrant gets inserted. The lower left rectangle that's been clipped. The lower right quadrant of the quadtree gets the lower right rectangle. The upper left gets the upper left. And the upper right gets the upper right. And we are done. So we cut this guy into 4 rectangles: lower left, upper right, lower right, and then they get inserted. This gets inserted into the lower right quadtree, lower left quadtree, upper left quadtree, upper right quadtree. So let's see if it works. It didn't crash, that's good, but we're not clipping anything. Okay, so let's add one more thing and see if it works. Yeah, let's get rid of it. Let's change you. So we'll change you to 49 to 51. 51 says it's going to be right over the main intersection point in the world. And it should subdivide into quarters. The top left will get 1, the top right will get 1, bottom right will get 1, and then the lower left one goes into the lower left subtree, which then gets passed on to the upper right subtree. And then that one is going to subdivide again, and hopefully everything should shake out. Or it might segfault. Who knows? Let's find out. Well, we didn't segfault. That's good. That's always a good sign. All right, so where are we? What's happening here? Okay. So that, insert these guys, subdivide. And then the lower left child goes from 0 to 3. I thought I got rid of those print statements. So if we have subdivided, if not subdivided, let's do it that way. So we don't care about the threshold. It is not. That's why I put that there, so you can see where the top is. Okay, so 0 to 100, boom, boom, boom. They go in there. Oh, I need a new line. Actually, we don't need to at all. Not subdivided threshold. Okay, so not subdivided threshold 3 contains 3. Subdivide, subdivide. Okay, so we've now got the guy from 0 to 100, his left child is 0 to 50, left child, left child, has min to 25, good, it's got 2 boxes in it, it's not subdivided, has a threshold of 3, currently contains 2. Left right child, it's not subdivided, upper left child is not subdivided, upper right child has, that's a problem. So this guy, the upper right child has, where do the other chunks of that go? So we cut it into quadrants. This guy picked up the piece of it. Oh no, it picked up the entire box. Oh, it's because interesting. So the upper right. Oh right. No, this is not good. It's not clipping properly. Because the max is 50 and it has something outside of its zone in it. Okay. So it's not chopping it properly. And the reason for that is because this guy is already. That's right. Yeah, that's why I should have made this a function, because this code here doesn't do the clipping. I added clipping down here. I added clipping down here, but this thing here isn't doing clipping. That's why. Okay. So all this should be pulled out and put into a function to clip and reinsert, basically. Okay. Clip and reinsert. All of that code will just get tossed into a private function. Clip and, yeah, you want to finish that, right? Thank you. Clip and reinsert. Const rect reference R. And basically that's going to have all that common code here, which I do not want to retype. Because what's happening is, like, if it was already in the data structure, it would clip it and whatnot. But whenever I got a new rectangle after it had already been subdivided, what's going on here? What did I do wrong? Subdivide, I need you is what I need. Center. There we go. And all the rest of that should work. Optimism. But I think it should, because it's all using our private memory variable. It should be fine. And so we just need to add it here. There we go. Beautiful. Beautiful. Worked right the first time. The second time. So you can see the our world. Let me sketch out the world one more time for you, so you can see that it is in fact working. So we've got our starting quad tree goes from 0, 0 to 100, 100. Okay, and so we insert a box from 10, 10 to 12, 12. It goes cool, fine. It's a box from 20, 20 to 22, 22. Cool, fine. 30, 30 to 32, 32. Cool, fine. These are these these three things here, when they get inserted into the Quadtree, nothing happens because it hasn't exceeded the threshold yet. Then we're going to insert 4040 to 4242. Then stuff's going to happen. So when we do this, then it cuts the world in half, cuts the world in half. Center point is 50, 50. And then it reinserts everything that's in its data vector, it reinserts into its children. And as it turns out, all four of its children are in the bottom left quadrant. So guess what? That's going to trigger recursively a that is not to scale. Like that. And so this center point is at 25, 25, like that. And then it recursively inserts these four things into its children. Two of them go into the bottom left, the left left of the left left. Two of them go into the upper right of the left left. And then we finish by putting one box right here. And so this guy gets clipped because he's over we've exceeded the threshold. So this chunk here goes into the upper left. This one goes into the upper right. This one goes into the lower right. And then this one goes into the lower left. But that one's already been subdivided. So that one bounces from the lower left into the upper right of the lower left. And then that part there ends up in the upper right of the lower left. And so if you look at it, the upper right of the lower left contains 4949 to 5050. So it's that little piece, 4949 is here, to 5050 is here. And so it's got that little piece, it clips successfully. Then the lower right child has this chunk here. The upper left child has this little chunk here. And then the upper right child has this little chunk here. And everything is hunky-dory. I am 100% confident this code is correct with absolutely no problems whatsoever. So, yeah. So I'll put it up on GitHub. So if you have a project where you want to be able to have a quad tree holding rectangles, and we got a little bit of supporting stuff here. We got points, we got rays, we got rectangles. Some classes for those. If you want that, I'll put it up and link to it on GitHub. And that is it for today. So that was two big-ish lectures. The first half was just setting up the stuff that we need. And then the second lecture was writing a quad tree, which miraculously worked right the first time, the second time. Yeah, I'm proud of it. And so that's it for today. I'll see you guys next time. Have a great Thanksgiving. Peace.